This lesson is a continuation of the Chapter 8 Hypothesis Testing series. So this is Lecture 8B. And we're testing claims about a mean in Part B. Now, Part A was hypothesis testing and testing claims about proportions. And when we test claims about proportions, we use z-scores, and now that we are shifting gears and we are testing claims about means, we are going to be using t-scores. When testing a claim about a population mean, ensure that the following requirements are met. The sample has to be a simple random sample, and the population needs to be normally distributed or greater than 30. And for all of our problems in this class, those two conditions are going to be met. So if they're not explicitly stated, you can assume that they are. Example 1, cell phone radiation. The chart below shows the measured radiation emissions corresponding to a sample of cell phones. Use a 5% significance level to test the claim that cell phones have a mean radiation level that is less than 1 unit. Assume the population is normally distributed. In this case, we are working with the actual raw data. So I'm going to ask you to pause the video and go to Stat, Edit, and put these data values in list 1. These data values are going to be the radiation emission levels for various cell phone brands. So pause the video and go ahead and put all of these values into list 1 and then return and we will run the test. Okay, the first thing they ask us to do is to write the null and alternative hypotheses. Remember, the null always takes the equal sign. And let's go back and look at what the problem said. We know we are looking at radiation emission levels, and we know that the alpha level is 5%, and the claim is that cell phones have a radiation level that is less than 1 unit. So the null is going to say, well, okay, the mean is equal to 1, and we're going to test the claim that the mean is less than 1 unit, and the alternative hypotheses will take that left tail claim. So hopefully by now you have entered the data in list 1. So what you're going to do is you're going to go to Stat, Tests, and select t-test. And since we are using the raw data from the lists, make sure that you select data for input. Then you're going to put 1 for the population mean, because that is what the null is claiming, that the average is 1. And make sure that you select the left tail symbol, because this is a left-tailed test, right? Because we're testing the claim that the mean radiation level is less than 1. And then you will hit calculate. If you look over here, I've given you sort of a snapshot of what your calculator screen should look like. And after you hit calculate, you're going to get a list of items. And the two that we're going to focus on the most are the t-value and the p-value. So the t-value is negative 0.4849, and the p-value is 0.3191. If we look at the p-value and compare it to the alpha level, 32% or 0.3191 is larger than 5%. In other words, the p-value falls outside of the tail. Anytime the p-value exceeds the alpha level, we will fail to reject the null. That means there is not enough evidence to support the claim that radiation levels for cell phones is less than 1 unit. Example 2, car crash tests. The claim is that for measurements of standard head injury criteria in car crashes, there's a claim that the average is 475 units. The sample size is 21, and there is a test statistic of negative 2.242, and we just want to generate the p-value. Well, before we generate the p-value, let's look at what's going on here. If we were performing a true hypothesis test for this on the mean, the null is going to claim that the average is equal to 475 units. And notice we're not doing more or less or anything like that. So we're going to let the alternative state the claim that the average is simply not equal to 475. So here's what we do on the calculator. We're going to select second vars. And we're going to select T-CDF. This is very similar to the normal CDF that we used for finding the area under a curve. But since we are doing means, we're switching from Z's to T's. So we will use the T-CDF. And your screen would look something like this. For the lower value, use that -5 because -5 is an extremely low t-value. And we're going up to -2.242. And the degrees of freedom is 1 less than n, which is 20. And then we paste, getting this value, 0.0182. Well, that gives us the value as you come in from t is -5 up to t is equal to -2.242. Since this is a two-tailed test, however, we have to double it to account for the area in the right tail, which gives us a p-value of 0.0639. So if we were performing an hypothesis test at the 5% alpha level, we would have a p-value that is larger than the alpha level, and we would fail to reject the null. Let's look at example 3, cigarette nicotine. The claim is that for the nicotine amounts in king-size cigarettes, the average is greater than 110 milligrams. The sample size is 25. The test statistic is 3.349. Now, since the claim is that the average is greater than 110 milligrams, this is going to be a right-tailed test. They give us the test statistic, 3.349. And we're going to do the same thing we did before, second vars, T-CDF. And since we're doing a right tail, we will start at 3.349 for the lower value. The upper value will be 5. The degrees of freedom is going to be 1 less than n. So 25 minus 1 gives us degrees of freedom of 24. And then we will paste. Notice this time we will not double the answer because this is a one-tailed test. So the p-value here is 0.0013, pretty much 0. So if we were doing an hypothesis test here, let's say at the 5% level, this p-value would be inside the tail. It's actually less than the alpha level. So we would reject the null. Example 4, pulse rates. The claim is that for pulse rates of women, the average is 73. They used a sample size of 40, and they generated a test statistic of 2.463, and we're looking for the p-value. Notice they did not make any claim that the average is greater than or less than 73, so we're going to do a two-tail. And when we do a two-tail, we're going under the hypothesis that the average is not equal to. Why not equal to? Because the average pulse rate for women could be less than 73 or greater than 73. And since they did not use greater than or less than, this is going to be a two-tailed test. And they tell us that the t statistic is 2.463. And if we do the right tail, we're going to go from 2.463 all the way up to t is 5. The degrees of freedom here would be 1 less than 40, which is 39. We would do the pasting. And again, since this is a two-tailed test, we will multiply by 2. That gives us 0.0183. Example 5, finding the t-critical values. You should recall from previous lectures that if we wanted to find the z-score for a given area to the left, we just did inverse norm, and we entered the amount of area to the left, and that would give us the corresponding z-score. We can actually do the same thing with t-values. So if you want to find critical t-values, it's the same procedure. The only difference is it's inverse t. Since we're doing averages instead of proportions, we will do inverse t. We will give the area to the left. In this example, I chose 0.05. But we always have to use the degrees of freedom whenever we are using t-values. And if you look back at example 1, we had 11 values, so the degrees of freedom would be 10. So your calculator screen would look something like this. You would hit paste, and you could draw the conclusion. In this case, we get negative 1.812, right, for the critical value. We can also use the confidence interval method. By now, you should be pretty familiar with confidence intervals. So let's say that we wanted to test the claim that the average cell phone radiation is less than 1 unit. We want to use a 5% significance level, which is a 90% confidence interval for a one-tailed test, because you would have 5% in each tail, and 90% plus 5% times 2, right, would give you 100%. If you want to use the confidence interval method, you just go to the calculator, you'll say stat tests, t interval, make sure it's t interval. And since we have the raw data from the cell phone radiation, we will select data. We will select L1 if that is where you chose to put the data. And then since this is a 90% confidence interval, you would do 0.90. Do not put 90. If you put 90 in there, it's going to give you some crazy results. So make sure that you put 0.9 for 90% confidence interval. And once you run it, they give you this interval. What does that mean? It means that we are 90% confident that the population mean for cell phone radiation is between 0.7071 units and 1.169 units. Since our interval contains 1, which is what the null hypothesis claims, since the 1 has been captured in the interval, then we will fail to reject the null. You might think of it as the null wins the argument. So that takes care of section 8.4. 8.5 is testing a claim about a standard deviation or a variance. Let's look at example 1. We have heights of models. The chart shows the heights in inches of supermodels. Well, if you look at the chart, these are the heights in inches. And they're testing the claim that supermodels have heights with a standard deviation less than 2.6. Now, I would assume that supermodels are almost cookie cutter in nature. They probably have the same height and the same weight. And that's basically what they're testing here. Evidently, the standard deviation in heights for women is 2.6, at least for this problem. Well, they're looking at these supermodels, and they want to see if the supermodel's heights is less than 2.6 in standard deviation. In other words, are the supermodels basically the same height? So at this point, I would encourage you to pause the video and enter this data in list 1. And after you enter the data in list 1, go ahead and run one variable stats, and you should generate a sample standard deviation of 0.7997. So pause the video and enter the data and run one variable stats and double check that you have that standard deviation. Let's go ahead at this point and state the null and alternative hypotheses. Remember, the null is always going to take the equal sign. So the null is going to claim that among the supermodels, the standard deviation in height is going to be 2.6 inches. The alternative hypothesis is going to claim, no, I think that their heights are a lot more uniform. So the alternative is going to say that standard deviation is actually less than 2.6 inches. We're going to use the chi-square test. The chi-square test is used whenever you are testing variance or standard deviation. And in this case, we are testing standard deviation. This is the formula for chi-square. Chi-square is found by taking the degrees of freedom, which is n minus 1. You multiply that by the sample variance, and then you divide by the population variance, or in this case, the assumed population variance. Notice that the null claims that it's 2.6, and that's what we're going to go with. So if you look over to the right, you can see where I entered 9, because we had, I believe, 10 supermodels. That would give us 9 degrees of freedom, the 0.7997 squared. That comes from the sample standard deviation, and then we divide by 2.6 squared. Notice that when you square the standard deviations, you should recall that that's actually the variance. So chi-square ends up being 0.851. If you use the chi-square table that's in the back of the book, and we will discuss that in class, or we have discussed that in class. If you use the chi-square table in the back of the book, you will see that the critical value is 2.088. But we generated a value, a chi-square value of 0.851, which is inside the tail. It's inside the critical region. We can also calculate the p-value for this darkened area here by doing chi-square CDF. We'll start at 0 and go to 0.851. And if we run it, we will see that the p-value for that darkened region is pretty much 0, which is less than 0.01, our alpha level. So the p-value is less than the alpha level. Whenever the p-value is less than the alpha level, we reject the null hypothesis. If we reject the null hypothesis, what does that mean? It means that the height variation for supermodels is less than the normal variation of 2.6 for women. So supermodels are pretty much the same height. Now, why did we use 0 here? Because the chi-square distribution starts at 0 and it goes forever to the right. So it does bottom out at 0. That's the first distribution we have seen that actually bottoms out. And this one, the chi-square distribution, bottoms out at 0. Okay. Another example, highway speeds. Listed below are speeds in miles per hour measured from southbound traffic on I-280 in California. This simple random sample was obtained at 3:30 p.m. on a weekday. Use a 5% significance level to test the claim of the highway engineer that the standard deviation of speeds is equal to 5 miles per hour. So the highway engineer claims if the standard deviation in speeds is 5 miles per hour. So that's what the null would claim, right? Because the null takes the equal sign. It doesn't say that we're testing a claim that it's more or less, so it can't be a right tail or a left tail. So we're going to go with different than 5. Different than 5 means that we have a two-tailed test. As before, we have to calculate the critical value for chi-square. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 12 data values. So the degrees of freedom would be 11. If we put all of these into one variable stat, if we put these speeds into a list and run one variable stats, we should get a sample standard deviation of 4.075. So we would put that in and square it. And then we will divide by 5 squared. Okay, and that comes from here, right? Because the null claims that the standard deviation is equal to 5. Once we calculate this, we get a chi-square critical value of 7.306. If we calculate on the left side, and we go from 0 to 7.306 and put in the degrees of freedom of 11, we get 0.2262. In other words, the area in the left region is 0.2262, but since this is a two-tailed test, we must double that result, and we get a p-value of 0.4524, which is a very large p-value. So what would we do in this case? Well, since the p-value is larger than the alpha level, which is only 5%, right? Actually, this is a 50% significance level. I misread that. If we go back and look at it, it says use a 50% significance level. That's probably a typo. Now, if we did use a 50% significance level, then in this case, we would end up rejecting the null. I have a feeling it should say 0.05. Let's make the change. If I can. .05. Okay, so if we use a 0.05 significance level, then obviously the p-value is larger than the alpha level, and we would fail to reject the null. Since we fail to reject the null, then we do not have enough information to conclude that the standard deviation of speeds is different than 5 miles per hour. Okay. Some key concepts about hypothesis testing. Chapter 8 is rather lengthy, and students tend to get caught up in, when do I use Z's, when do I use T's, and all of the different software that we run to do the hypothesis testing. So I wanted to close with some key concepts when it comes to hypothesis testing. Remember that we use z-scores if we are testing proportions. We use t-scores for testing means. The t-score is always going to require the use of the degrees of freedom, which is 1 minus n. And we use the chi-square distribution if we are measuring variation among data. For example, we looked at the variation in heights of models, so we had to use chi-square. Also realize, again, that the chi-square distribution starts out at 0. So chi-square values are greater than or equal to 0. They are never negative. And that's a first for us. That concludes our lesson on hypothesis testing. Thank you.